So today I am planning to talk about this thing, or it's slightly difficult to even say what it is, this thing called singular value decomposition. Compared to the age of the area data science, this is like way too old, this is like almost like the grandfather of grandfather. People used to know what is a singular value decomposition, I think starting from 1870s. Okay, so it's like such an old thing, but like many surprising things in mathematics, it starts finding new applications, almost even new insights as things progress. Okay, so it's a classical thing in math, but recently it's also considered as, many people call it the best view to understand it. Okay, so it's a very tall claim. How something that has been in use in the area of bilinear forms, operator theory, etc., from that time suddenly becomes the best tool to really understand what your data is saying to you. Okay, so since it's such an old tool, I have to start with a warning that I am only going to give one view of what is singular value decomposition. It has multiple views. It's like that story of the blind people looking at the elephant from different parts and seeing different sides of it. Okay, I'll hint to what is the more historically original view of singular value decomposition maybe in the second lecture, but in this lecture I am going to view singular value decomposition as from the perspective of a data science view. Okay, this is not the classical view, but it's a very useful view to have. Okay, so yeah, this is both the reading test and also you are really good with your responses in the first lecture. So please try to read this and raise your hand if you understood what this slide says. Okay, this setting we will have throughout the lecture. Okay, so it's mostly to have a standard notation so that I don't have to every time say what is capital X, what is small x, and so on. So think about data points, think about really points in the space. We have n number of points. Okay, I'll keep these notations consistent. This little n will always be the number of data points that we have, but these points are not points necessarily in three-dimensional Euclidean space. The dimension we keep it arbitrary. It could be some parameter d. Okay, so we have n points in a d-dimensional space. So remember that I will use d for dimension of the space and n for the number of data points. The set of points I will denote by capital X, and the individual points I will denote by x1, x2, x3 all the way up to xn. But why I am stopping, and I want you to make sure that, and I want you to really register it in your mind that x1 itself is a d-dimensional vector. x2 itself is a d-dimensional vector, right? So for example, xi you should think of it as a d-component vector like xi comma 1, xi comma 2, xi comma d. Okay, I am not going to use the typical overbar notation for a vector. Many undergrad courses will usually distinguish a scalar and a vector by putting a bar over the vector. I am not going to use it because mostly we are going to deal with vectors. I will fill the slides with bars if I start using a overbar for a vector. One thing. Second, some point that can result in a confusion is that usually when you write x with a subscript, even people who are used to the non-barred notation might assume that you are talking about a scalar. Okay, but no, even x1 is a vector. If I say x1 comma 3, it will be a real number. Okay, so this is the setting. These points are given to you, and what are singular vectors of this collection of data points? What are the singular vectors of x? This is what I claim. Okay, we are looking for an orthonormal basis of the embedding space. The embedding space is r power d, the d-dimensional Euclidean space. We are looking for an orthonormal basis for this space with a peculiar property. Okay, in fact, it's a very our demands are so high. We are not looking for one property. We are looking for d properties at the same time. Okay, we will order this basis in a particular way. I have written v1, v2, v3, etc., vd, such that if I take the span of the first vector, that will give me the best one-dimensional space that approximates the data. If I take the span of the first two vectors, it will give me the best two-dimensional space that approximates the data, and so on. Okay, so this is what singular vectors of data mean. If you understood, please raise your hand. Okay, so you all guys can almost leave for the rest of the talk. Okay, this lecture is going to be about explaining what is there in this slide. Okay, so I mean it's those who already know of it may get some new insights, but this is okay. If you do not understand this, then that's the people whom I am mostly addressing it to. Okay, I want to. In fact, this is also going to be the last slide of this lecture. Okay, so after this lecture, I hope you will have a clearer understanding of this. Okay, so we are set to go. We are set to go. Okay, so let me see. Let me test your imagination a bit. Okay, can you imagine vectors in r to the power 1 million? Okay, can you imagine points in a 1 million dimensional space? If you can, please raise your hand. Good, good, 2, good. Okay, so others find it a bit difficult to imagine. Okay, the trick is with the word imagine, almost nobody can visualize, right? If you mean imagine to be visualize, then I don't think anybody can visualize points in a, forget 1 million dimension, you cannot visualize points even in a 4-dimensional or a 5-dimensional space, right? But your imagination needn't always be a visualization. Okay, in fact, there is this famous joke / conversation between a physicist and a mathematician. The physicist claims, oh, I can, with so much of training in physics, I can now visualize 4-dimensional space, but visualizing anything more than that is difficult. And the mathematician says, like, I can visualize a 1 million dimensional space without any difficulty. And the physicist asks, how? He says, I just visualize Rn, the n dimension, or Rd, the d-dimensional space, and substitute d equal to 1 million. Okay, so that is the kind of imagination that we are speaking about. Okay, so you should not get, you should not shut yourself down when people speak about points in a 1 million dimensional space or a 10-dimensional space. Okay, it is mathematically very simple, and even visualizing it to some extent is possible. Okay, so that is where the second question comes. Okay, there is always this dichotomy between how a physicist will view a vector versus how a computer science person will view a vector, right? The physics picture you would have all studied in your high school, right? You have a vector which is like an arrow with a tail and a head, right? If you have your coordinate system, this would be your physics view of a vector. Okay, and what is the, by the way, we'll always insist that our vectors have their tails at the origin. Okay, we are only going to think about vectors whose tail is at the origin, head is arbitrary. The computer science view of a vector is thinking of this just as an array of points. Okay, so this might be something like 2, 1.5. So the computer science view would be just thinking of this like a 2, 1.5, or better still, you think of it as a column vector 2, 1.5. Okay, so the computer science view of a vector is just a list of numbers. It's very simple. The physics view of vector is this geometric picture. I think it is time that people also talk about this third view, or the data science view of a vector. What would it be? Data. Yeah, data, but still the picture would be of a point. The data science view of a vector would just be, this point to which we the head of the arrow. Okay, so let me say there are 3 views of a vector. Okay, the physics view is that of an arrow with tail at the origin. The data science view is that of just a point at the location of the head, because anyway the tail is fixed, you can always complete it to a vector, there is no information lost. And the computer science view is as a list of numbers. Okay, which view is better? Point view is better. Any differing opinions? Depends on the need. Correct. In fact, this question is a tricky question. You should have all the 3 views with you. You would not know which is going to help you with which problem. Okay, and it's important that you can seamlessly transition between one view and the other. Okay, and we will be doing that all through this lecture. Okay, we might think of it. For example, when you want to think about distance between two things, the data science view of it as points is very useful. Even more, if you want to identify clusters of data points, surely the point cloud view, viewing vectors as points in this appropriate dimensional space, is going to be immediately tell you, okay, what is the picture you should have when you think about a cluster. Okay, but think about something like, we heard about cosine similarity, or rather the angle between two data points. It's more convenient, at least in the beginning, to think of the physics view with the full arrow, so that any two arrows will lie on a plane and there is an angle between these two arrows. So when you get into a bit more of geometry, this view of the physics view might start helping. And when you think about lot of operations, like you want to add vectors or do some amount of processing with them, or even think about how you will finally implement all your idea on a computer program, the computer science view will also really help. Okay, so like for example, how you would add two vectors. The computer science view is the easiest if you are writing a program, right? You just have to run one loop and then keep adding it term by term. The result will be another vector, which is this. The physics view, you have to do the parallelogram though, right? If I want to add this v with another vector u, okay, maybe this is bad. Okay, if I want to add it with another thing called u, I do this parallelogram, and this will be the result of v plus u, right? We know it's the same thing. What the point by point addition inside the for loop will do is exactly what the parallelogram law will do. Okay, but this gives a different feel to it, this gives a different picture to it, so it's important that you understand vector addition in terms of both. Same thing about scaling and linear combinations and so on, right? And also, when you are thinking about rotating things, right? When you are thinking about rotating a point cloud and so on, I do not know. Some people prefer to have the physics view. Some people prefer to have the point cloud view. But the physics view is a bit more foolproof because you really know where the origin is, and so the rotation is very clear. Whereas in the data cloud view, it may be a bit difficult. Computer science view is like really difficult to appreciate what rotation will do. Okay, so you have to keep in mind these three views. And one operation that we will be using extensively in this lecture is that of a projection, or more correctly what is known as an orthogonal projection. Okay, so projection is something like, you have a vector v like this picture, and its projection along the x-axis is you drop a perpendicular to x-axis, and this vector that you get here is what is called as v, and this I will say as the projection of v along the x-axis. Okay, I will write a vertical bar, and underneath it I will, okay, I am writing too small a font. Okay, I will change that from now. Okay, so this is the idea of projection. By the way, it's very difficult for me to draw 3D pictures. Okay, so most of the pictures I draw will be 2D, but this is a practice that you should cultivate. First, look at the 2D picture that I will draw on screen, and then try to imagine what will be, try to visualize what will be the 3D equivalent of it. Okay, so in the 3D equivalent of it, if like the surface of this table, let's say, is a 2D plane, and you have, say, this corner is the origin, and if you have a vector, this corner is the origin, you have a vector sticking out of it, do you see in your head what is the projection of that vector onto the plane, that is the tabletop plane? It can be a point, it can be a physics vector, it can be an array of numbers. Okay, all three are equivalent to me. The question is which point? It's not the origin. Okay, the projection of this point on this flat horizontal surface is not the origin. It needn't be on x-axis, but very good point. It is somewhere on the xy plane, I agree, but which point on the xy plane? Exactly. So that's a word I was fishing for. You drop a perpendicular from your point to the plane. Now it's no more dropping a perpendicular to an axis. You can really drop a perpendicular to a plane. In fact, if you drop a heavy object from that point, since gravity is acting in this particular direction, where that heavy object will fall is the orthogonal projection. To make it mathematically precise, the projection is that point from which if you connect to the original point. Okay. So my drawing in 3D will surely be bad, but let me still make an attempt. Okay. So if this is a plane and you have a vector v like this, when you drop a perpendicular, it will fall somewhere here. But what is the key defining point of that? Okay, this was not needed. What is the defining point of this is this vertical dotted line here and this plane are going to be perpendicular. Okay. So you understand when a line is perpendicular to a plane, right? Which means any line you draw on the plane, this vertical line is going to be perpendicular to that. Okay. And this blue point here is called the projection of V, and let's say if I call this surface as some S, this vector here I will denote it as V's projection onto this surface. Okay. Any other interesting property about this point?
Shortest distance.
Exactly. In fact, this is the point on the surface that is closest to V in terms of Euclidean distance. Okay. We'll come back to this point once more, but I really first want you to be able to visualize projection in 3D. Okay. And imagine projection in 1,000,000 dimensions. Okay. So this projection is also an operation that kind of carries along. For example, the easiest way to talk about projection when you are in some 5-dimensional space and you are looking for projection into a 3-dimensional subspace of it is to look at the point that is nearest to the given point, nearest in the sense of Euclidean distance. Okay. So in fact, how many of you are comfortable with this idea of subspace? That's the last slide. I think I should have. Yeah. How many of you are comfortable with the idea of a subspace? What is a good? Okay. So what is a subspace? It's a vector space. Yes. But let's say in 3D, let's stick to the ambient space as being 3-dimensional. We will try to build our visualization there. What are subspaces in 3-dimensional spaces? Yes. Yes, but what is the picture that comes to your mind?
Any 2-dimensional plane should be a subspace.
Yeah. It is, the answer is actually wrong. Okay. Any 2-dimensional plane is not a subspace in RD, but some 2-dimensional planes are. Which 2-dimensional planes are? They are perpendicular to what? No, that's also not the correct answer, but we are moving in some direction. There is
The XY plane or the YZ.
yeah, those are examples. XY plane is a 2D subspace. YZ plane is also a 2D subspace, but they are not all. In fact,
Two vectors in the space, then their linear combination
yeah.
is also to be the same.
Correct. This is the perfect definition. I will come to it, but I want to first make sure that everybody has a picture in mind. You are 100% correct, but we will see why that.
That is parallel to any of the axes.
Yeah, that's also wrong. Okay. Exactly. Okay. This property, thanks that it took so much time to come, but I hope that will help drive it in. Okay. We are only talking about when you say subspace, it's a plane passing through origin. Okay. So in the 3D, if you can visualize, let's say this point in front of me is the origin. I could draw a plane like this. That's not a subspace. A plane like this, it's not a subspace. Even if it's a horizontal plane parallel to the XY axis, it's not a subspace. The plane has to contain the origin. Okay. So 2-dimensional subspaces in this context are precisely planes that pass through the origin. Okay. And I'll tell you why it is so. That is because of the definition that was given. Any 2-dimensional subspace you can generate by taking two vectors. Okay. Two vectors, like remember that the tail of both the vectors are always at the origin, and then look at all the other vectors that can be generated as weighted combinations. Technically these are called linear combination, which is another way of saying a weighted sum. A weighted sum of these vectors. Weights could be negative also, so you can really Okay, that picture I hope you already have, but otherwise I think let me take some time to digest that. Okay, so this is the origin. You have one vector like this and another vector like this. Okay, do you see that these two vectors together will be on a single plane? Why? Because there are only three critical points: the origin and the tail of first vector and the head of first vector and head of the second vector. These 3 points define a plane. It is that plane that we are going to talk about, and in fact the most important mathematical property of the plane, this particular plane, is that all the vectors in this plane, all the points in this plane can be written as linear combination of these two vectors. What is linear combination? Some alpha times the first vector plus beta times the second vector. Okay, so this is what is called as the span of these two vectors. It's the plane which contains these two vectors. Okay, so subspaces are, one way to define subspaces is that is why this is a subspace. Okay, this is the case. But these are not all the subspaces. In fact, the three-dimensional space also contains one-dimensional subspaces. What would they be? Lines, yes, and again passing through origin. For the same reason, this time we will just take one vector and take all this line that is all scalar multiples of that. If this is v, then alpha times v for any real number alpha, including negative, 0 and positive. Okay, so three-dimensional spaces can have two-dimensional subspaces which are nothing but planes passing through origin, one-dimensional subspaces which are lines passing through origin. It has a three-dimensional subspace which is itself. It is like saying a set is a subset of itself. Similarly, every space, as we call it vector space, is a subspace of itself. So there is one three-dimensional subspace, only one, but there are uncountably many two-dimensional subspaces, uncountably many one-dimensional subspaces. There is also one zero-dimensional subspace which is just the origin. That's a single point. Okay, don't worry too much about that. Okay. There is also a very interesting or useful property of subspace, and many people will define subspace that way. I call it the trap property or the closure property. Okay, if you take two vectors from a subspace and take any linear combination of them, in particular you add them, the answer will also lie in that subspace. Okay, so you think about this plane that is containing these two vectors. We said that's a subspace, it contains the origin because the tail is in the origin. Now you take any other 2 points in this plane and do any linear combination of them, answer will be in the same plane. You really cannot come out of the plane by doing linear combination. Okay, so the addition, if you think about the parallelogram view of addition, it should be clear, because the parallelogram that you are going to draw is going to be in this plane. So the diagonal of the parallelogram is also going to be in this plane. Okay, so subspaces, in fact this is the better definition for subspace in many sense. It's a subset of a vector space which is closed under linear combinations. Okay, this closure is a very critical property in defining objects in mathematics, so that you do some operation on that and you are confident that the answer will be another element in the domain that you are doing. Okay, so roughly all of you are with me. Okay, if you have any doubt regarding subspace, please ask me, because as I hinted in the previous slide, SVD is about subspaces. Okay, so you have the picture of two-dimensional subspaces in a three-dimensional space. Okay, that's the most important picture you should have, but you should also know that that's not the only possibility. The lines through the origin, the one-dimensional space, gives you another kind of imagination. Okay, now again, for those who can imagine higher dimensional spaces, you can think about like a 4-dimensional subspace of a 10-dimensional space. Okay, it is still possible. Again, the mathematical way to approach that would be, okay, this 4-dimensional space, how do you pinpoint a 4-dimensional space? You need like some 4 vectors. Okay, how do you pinpoint a 2-dimensional space? To give a plane, it is enough to give 2 vectors in the plane, because 3 points will come that uniquely defines the plane. Similarly, to define a line through the origin, 1 vector is enough. It's all the points along that vector. Okay, in fact this is how a computer program or even any formal mathematical analysis will talk about a two-dimensional subspace. It will talk about two vectors whose span will be this, okay. And it is even better if you use perpendicular vectors, okay. Instead of just taking vectors like this, most of the time you will take vectors like your x-axis and y-axis, or maybe the rotated version of x. And then when they are perpendicular, you call them orthogonal vectors, okay. Orthogonal is another word for perpendicular, orthogonal vectors. Similarly, for three-dimensional subspaces, you can pinpoint three-dimensional subspaces by giving three orthogonal vectors, okay. And these vectors, even when they are not orthogonal, if there is something called linear independence, which I won't get into now, if they have enough stuff to span the subspace that you are talking about, we call them the basis of that vector space, okay. So whenever we are talking about a subspace, most of the time to describe that subspace, we will be describing it in terms of, if it's a d-dimensional subspace, we will describe it in terms of d vectors. Most of the time these d vectors will be orthogonal, not necessary, but that makes our life very easy. Even more, we will make it unit length. So these are going to be a collection of vectors which are all of length 1, and they are all going to be perpendicular to each other. And in this case, we will call them an orthonormal basis, okay. So whenever we are talking about subspaces, if you want to pinpoint a subspace, the best way is to give an orthonormal basis, right. So what is in the three-dimensional space for the x, y, z thing? What is an orthonormal basis for the xy plane? Yeah. Yeah. So for the 0, 1, 0, like I'm thinking about x, y, z in this order. These two vectors, right? If I kind of draw it here, this will be my 1, 0, 0, and this along the plane. Right, along this plane, this will be my 0, 1, 0. These two are one candidate for orthonormal basis, but remember, it's not the only choice. In fact, I can rotate both of them together by some 30 degree, I'll get two new vectors, they also form an orthonormal basis, okay. So you should have the picture of a subspace as a plane or a line passing through the origin. You should also have the idea of this orthonormal basis. Physics people also use it, your I hat, j hat and k hat, right? They form an orthonormal basis for the three-dimensional space. They are not the only combination. In fact, the axis, choice of axis is arbitrary. You can kind of rotate these three vectors whichever way without changing their length and their mutual angle, they remain orthonormal basis, okay? And this idea also extends to 1 million dimensional space, right? So when I am talking about some k dimensional space, the only way I will talk about them is by giving k orthonormal vectors that will generate this space, okay. So this terminology is critical. So with this, if you go back and read, except for the best fit part, I think you will be able to appreciate more of this. The span of a vector, the first bullet point, span of V1 is just all the scalar multiples of V1. Some alpha times V1, where alpha could be any real number, both negative, 0 and positive. So it will be a line that kind of passes through V1, okay. So your SVD, if your SVD is V1, V2, Vd, first of all, SVD is a set of orthonormal vectors. So in fact, this is going to be one orthonormal basis for the entire space, the d-dimensional space, okay. As I just mentioned, there are multiple options for orthonormal basis. You can take the ijk and rotate it in whichever way you want. You will start getting different choices for orthonormal basis. Let's think about SVD in 3 dimensions, d being 3. We have to find 3 vectors, some new candidates for I hat, j hat and k hat. This won't be in general the original I hat, j hat and k hat. This is going to be some rotated version of I hat, j hat and k hat. Let me call them V1, V2 and V3. These are unit length, they are mutually perpendicular and they have a very useful property. V1, if you take V1 and take the line that is running along V1, the line through the origin which runs along V1, which is a one-dimensional subspace. That is in some sense the best fit one-dimensional space for your data. I will define what is best fit in the next slide, but forget about the best, think about it as something which is very good for this data, but this is the one-dimensional thing that is best fit for data. So if you want a very coarse approximation to your data, this will be what you will use. Now you take the second vector in this new orthonormal basis, V2, which might be where after you do some rotation your j hat might go. V1 and V2 together, V2 in itself doesn't have any, it has, but again, it's not a first level property, but V1 and V2 taken together, okay, there will be two vectors, both, anyway, all the tails are at the origin, so they are perpendicular vectors, so there is one plane spanned by them. Spanning the plane spanned by them is nothing but the plane that contains both of them, okay, and that plane spanned by them turns out to be the best two-dimensional approximation for your data, okay. If you project your data into this space, then you lose least amount of information. That's the formal, the best fit I will anyway take 5-10 minutes and define. Similarly, in the three-dimensional case, once you get to V3, there is nothing useful being said, because V1, V2, V3 will span the entire space. So this is the original space itself. This is surely not just the best fit for your data, this is a perfect fit for your data. You are not losing any information, okay. So I hope you are understanding more of this slide, and this terminology is also with you. Idea of subspace and how a collection of orthonormal vectors can uniquely define a subspace is critical. Please do ask me if any of this point is not clear. Okay. So now in the next 2-3 slides we will formalize this idea of best fit. Okay. So we will start with the notion of distance. Okay. Distance between 2 points is something which all of us know, okay, but again that's actually not a correct statement, because there are multiple different alternative definitions for distance. You would have, because it's a data science course, you would have already seen many, right? Euclidean distance, which I am writing it here, is just one example of them. You could have Jacquard distance we saw for sets, right? You can have L1 distance or Manhattan distance for points in plane. This 2, if you replace in the summation, this xj minus yj, the whole power 2, if you replace with 3 and you take the cube root, then you magnitude to the power 3 and you take the cube root, you get the L3 norm. If you replace it with some p and you take the pth root, you get the LP norm. So there is a lot of distances, but in this lecture, and in fact in the entire SVD literature, we will stick to the Euclidean norm, which translates to our geometric idea of distance. Okay. So recall that now in this picture x and y are d-dimensional vectors. So when you calculate the Euclidean norm, it's going to be a sum of d values, each value being the square of the component wise difference. Okay, I'm sure all of you understand what is a Euclidean distance. Okay, but you can also use this distance to talk about distance between a point and a set. Okay, first it was point to point, now it's point to a set, and there the standard definition given is the distance from a point x to a set S is among all the distances from x to points in S, find the smallest one. Okay, so this is distance from x to the nearest point in S. That's the idea of a distance. Formally, it is minimum over all points in S, d of xy. Though I say formally, this is not correct. You should technically use what is known as an infimum, because if your set has like open boundaries, then the minimum may not exist. Think about what is the distance between the origin and the open interval 1, 2. Okay, so you might need infimum and all in a calculus kind of setting, but for our mental picture, it's the distance to the nearest point. Like if you were on this point and you want to jump to this set for life, this is the point to which you will jump, because that's the shortest distance. Okay, the geometric intuition is what is important. Now in our context, the set S is always going to be a subspace. Okay, that's the third picture. The definition remains the same. It is in fact the distance to the nearest point. It's distance from x to its nearest point in S. Okay, But when it comes to this case, when S is a subspace, you can also give a further geometric interpretation to it, that it will actually, the point which is closest to it, which in this case is this orange point here, if you join X and this orange point, it will be perpendicular to this subspace. Okay, I have drawn this subspace now as a line through the origin, but in your mind you should imagine it as a plane through the origin. Okay, and then the point X, let me call this X's projection on S. Okay, the line joining X and X's projection on S will be perpendicular to the S itself. Okay, don't get fooled by the 2D picture I have drawn. Imagine it in 3D and then see that, where, and also imagine an inclined plane. In the beginning I asked you to imagine a horizontal plane. That's a slightly easier case to imagine, because if you drop an apple from X, it will fall at X projected onto S. But if it's an inclined plane, the apple will fall somewhere else. Okay, your perpendicular has to be drawn, it's not the perpendicular needn't be vertical. It's perpendicular to the plane. Okay, so I want all of you to be able to imagine what is this projection even when S is a inclined plane through the origin. Is the picture clear? Okay. So this distance then turns out to be the distance of this perpendicular that you drop. Okay, by definition. But this is still not a best fit k-dimensional subspace, because we are in this slide we are still only talking about one point. Okay, but our data, remember, we have n data points, not one. Okay, so yeah, we still want one k-dimensional subspace, but we want something which is good for not just one data points, but for n multiple data points, x1, x2, all the way up to xn. Now this idea is standard. Okay, I mean each point will have some distance to a plane. Now in order to quantify how good this plane is for this n data points, you will have to accumulate all the distances or errors or something, right? You either add them up, or you take some weighted combination of them, or you take the maximum. Okay, in this case we just simply add them up, but not directly, we add the squares. Okay, so the error that we are going to now talk about is, like, if you have n points x1, x2, etc., xn, you take the distance of x1 to S, square it up, you just take x2 to S, square it up, x3 to S, square it up, and add all these up. Okay, this has reasons because it makes it very easy to do calculus on it. You can differentiate and take the because what is the most ugly thing in the definition of distance is this power of half, the square root. Okay, that makes it very ugly when you want to optimize it, differentiate it, and so on. So by squaring it, you are getting rid of that square root, and hence the whole thing is going to be polynomial. You can easily differentiate and so on. Okay, so the error that we are talking about now, remember, in order to talk about error is a function of two arguments. One is the data collection, the data set X itself, and S is some subspace. Okay, some k-dimensional subspace in a d-dimensional ambient space. Okay, the distance or the total error of the data point to this subspace is just sum of these squared Euclidean distances. Okay, and each distance, remember, is the length of the perpendicular that is being dropped from that data point to this subspace. Okay, so is this first box, the idea of error, clear? Okay, the one-dimensional picture, or the the picture I can draw of this will be like this. In this picture, the ambient space is two-dimensional. The subspace I am taking is one-dimensional. The points are x1, x2, x3, x5. Each of this d1, d2, d3, etc. denotes the distance of the corresponding point to the subspace, and the error that we are talking will be d1 squared plus d2 squared plus d3 squared all the way up to d5 squared. This is the total error that we are. Okay, this is a sum of squares of errors. Okay, this is the idea of error, and then when you talk about best fitting, we talk in terms of minimizing this error. So this was again this was a definition term we had in the first slide. What is a best fit k-dimensional subspace for your data? It is that k-dimensional subspace which minimizes this total error. Okay, so it's a least total square error plane. Okay, this is the definition of best fit. Okay. So this, I hope this argument is just, why, what is this minimization running over? The argument x is given to you, that's the data that is given to you, you don't have a choice on that. S is what you choose. So this argument, that subscript, you are actually searching over all possible k dimensional subspaces. So if you are imagining in 3D and S is 2D, you are running your optimization over all possible planes that pass through the origin. Okay, all 2D subspaces, all planes that pass through the origin, all kind of inclinations and so on, including the horizontal, the vertical, everything in between, right? And among all these planes, you check which plane minimizes this total error as defined in the first box. That plane, that is what is the argument. It is not the minimum value of the error, it is the argument, the S that minimizes the error. Okay, that is what this argument stands for. If I had just written minimize, min instead of argument, it is a value. What is the minimum error? I am not interested in that value, I am more interested in which subspace minimizes this error. Okay. Is the second box also clear? Oh. So in this picture that I can draw, which is the S that I will pick? In this case, it's a two-dimensional ambient space. So one-dimensional and S has to be one-dimensional for this example. If S is one-dimensional, then what are one-dimensional subspaces in a two-dimensional plane? All the lines that pass through the origin. Okay, don't forget that. And among all the lines that pass through, so now it's very easy to do a search. You can just take one line and rotate it 180 degrees. You will get all the possible lines, right? Now do this 180 degree rotation, and every time you make a move, calculate what is the total error, d1 squared plus d2 squared. d1, d2, etc. will change based on the orientation of this line. So your total error will also change. There will be one or more points where this is the minimum possible error, and that line, one of those lines, it needn't be unique. There would be, for example, if all your data points were kind of in a circular fashion around the origin, then every line will kind of, it's a very symmetric structure. Every line will be equally good. So the best fit subspace needn't be unique, but among all the guys which minimizes this error, you pick one of them. Now, one of the lines with the minimum error. Is this thing in your mind clear? Can you visualize the same for 3D? Okay, so imagine what would be the best fit two-dimensional subspace for the Milky Way galaxy. Okay, so I really want you to imagine the Milky Way galaxy with all the points, all the vectors are stars in the galaxy, right? Can you imagine that? What would be the 2D subspace that is best fit? Actually, I should have put these questions in the next slide. Okay, you can answer this question only if I tell you what is the origin. Okay, so because we are only looking for planes that pass through the origin. So what is the center of Milky Way? Let me check how good you are in general reading, physics. What is at the center of, by the way, what is center of the Milky Way? How do you define center of a point cloud? Okay, you just have to add all the points, vector addition of all the points and divide by the number of vectors. It's just the average, component wise average and so on when it comes to point clouds. But when you talk about Milky Way or this astronomical things, it's not you don't consider each point as just a point, you consider it as a point with its mass. So when you say center of a Milky Way galaxy, it's actually the center of its mass. You will have to do a weighted addition. The sun is going to only have a very small impact, whereas a much larger star is going to have a much larger impact in deciding what is the center. So what is the center of mass of Milky Way? So it's a very big thing, like I think 2018 it was pictured. It's a black hole called the Sagittarius A. Okay, it's a very massive black hole. I think some 28,000 billion light years away from Earth or something. That number may be wrong, In the astronomical scale, I kind of always get confused with this thing, right? So it's a black hole, and there was this Event Horizon Telescope 2018, 2019, which could actually picture the black hole. Okay, so that's our center, that's our origin. The Sagittarius A black hole, or the center of Sagittarius A black hole. So if that is the center, which would be the best fit two-dimensional subspace for Milky Way? What is the shape of Milky Way? It's a spiral. It's not elliptical, but you're correct in another sense. In fact, ours is a very flat galaxy. It almost looks like an idli or rather a thick dosa, right? It's not three-dimensionally equally spaced. So in fact, there is a natural two-dimensional space. If you kind of take that subspace which goes along this, it's like cutting the idli, like slicing the idli very carefully, right? As if you are going to make a sandwich out of it, right? It is that kind of a slice which would be the best 2D fit for Milky Way galaxy. If you have to draw the picture of a Milky Way galaxy on a screen, this is the best 2D space that you should take, so that the whole stars will now look like a spiral that you can see going around this plane. Whereas if you take a 2D subspace which is kind of 90-degree shifted, the entire galaxy will look like a single strip of a line. That's not the best 2D subspace for this, right? So this is the picture I want you to have. When you are talking about this best fit 2D subspace, it is the most, like if you were going to draw this in 2D, that is the space you will choose. It's like minimizing this error, total error and so on is the mathematical way of making it precise, but it also has this visual thing. Okay, so I hope you can now imagine at least the best 2D subspace for 3D data, right? And this picture you should have in mind even when you are trying to find the best 5-dimensional space for 20-dimensional data. Okay, you may not be able to visualize it, but the idea is the same. Okay, so this picture is very important. Okay, again I'm saying the same thing over and over again, but that's what we mean by best fit subspace. The formal definition is this, but the imagination, the picture of this Milky Way galaxy and the plane going through it, which generalizes to any 3D point cloud, is equally important, right? You capture almost all the information in the data on a limited budget. The budget is the dimension with this. Okay, that's why in fact the subtitle for my talk was the nearest low cost accommodation for your data, where cost being the dimension of the subspace that you want to work with. Okay, in the context of applied data science, this dimension will really come and hurt you in terms of how much computation you have to do, because computing a Euclidean distance between 2 points is actually, there are d squarings that you have to do, right? And the d multiplications that you have to do, these d multiplications are what you are going to cost. So if your data comes in 1 million dimensional spaces, which is very typical now when you think about document frequency vectors and all, the dimension that you start with is number of words in the English dictionary, which is roughly like 100,000. So data comes in this 100,000 dimensional space, and if you start computing distances directly there, you are going to take a lot of computation time. So it's very important to be able to represent this data in a much smaller dimensional space, like a 20 dimensions or 50 dimensions, without sacrificing too much of the information. Okay, that is why these low dimensional representations are important, and the cost here, the budget that you are working under is this. Okay. Everybody is now able to imagine the best fit subspace, at least 3D, 2D and all, right? Actually, if you ask what is the best fit one-dimensional subspace for Milky Way, again with the same center, I think it's not unique, because within this plane it is almost circularly symmetric. So almost every line, every rotation that you take will almost look the same. Okay, and also think about, this is also an important visualization. Let us say instead of taking the center of Milky Way as the origin, I move to another galaxy somewhere or somewhere in the outer space way outside of Milky Way and pick that as the center, then this might change. Like for example, if this new origin that I fix is somewhere, if the Milky Way galaxy, this is the best fit subspace for the Milky Way galaxy, and I take a point somewhere here, then unfortunately, since now the 2D subspace has to pass through this origin, it really have to slice the Milky Way. It cannot take that best, the earlier best. Okay, so actually insisting that the plane passing through the origin, plane should pass through the origin, comes at a cost. Okay, in fact it's not, and in data science, I'll talk about that in the next lecture. There is a very useful tool called principal component analysis, which first thing it does is it centers the data, which means it finds the centroid and subtracts the centroid from all the data points, so that it is, in some sense, you translate your data so that the origin is in fact the centroid of the data, and then you find the best 2D subspace. Okay, that's what is called the principal component analysis. This is in some sense more useful if you are in really a low dimensional budget. But if you are okay, if like 20 dimensions and 21 dimensions are okay for you, then SVD without the centering will not be very much of a help. You just have to pay one extra dimension. Okay, and I already hinted about it's not necessarily unique, especially you can see it if you look at what is the best fit one dimensional subspace. Okay, now this picture, as I said, is the starting point, but I'll bore you again. There is one more picture that we have to see for the same thing. Okay, the alternative. Okay, and here I am going to use Pythagoras theorem. Okay, so remember this picture here, you are always talking about this distance of x to its nearest point on the subspace, and we saw that, we mentioned that you drop a, how do you get that point? You drop a perpendicular from x to s, and the point where the perpendicular hits s is the projection. You can think of it as a point or as a vector with the whole thing, right? Now our error, if you remember, was d squared, this distance squared summed over all data points, right? Now let's focus on the distance for one point x alone and use Pythagoras theorem. Okay, so you are seeing a right angle triangle here, right? Distance is one side, the length of the projection is the second side, and the whole vector itself, the original vector itself, is the hypotenuse. So Pythagoras theorem will tell you that the hypotenuse square is sum of the side square, or written in another way, distance squared, which is what we are summing up in our total error, can be expressed as the difference of the hypotenuse square and the projection length square. Okay, simple Pythagoras. But now add it up for all the data, n data points you have, you add it up, what you get is okay, so sometimes there are two ways to write this summation. I could have written this summation as sigma I equal to 1 to n d squared of xi comma s, which is also same as saying sigma x element of s d squared of x comma x. Okay, it's only about how the first one is more like a C syntax, what I have written in blue. The second one is more like a Python syntax. You can really iterate over a set. Okay, for each element in the set you calculate the squared distance and add it. Okay, now substitute for each distance squared what you get from the Pythagoras theorem. It will be length of x squared minus length of its projection squared, split the sum into 2, and this is what you get. Okay, sigma x element of x, the length norm squared, this double bar just denotes the length or the norm of the vector, length squared of each vector minus a similar summation. This time it is the length squared of the projected vectors. Okay, what is special about this summation? What can you say about the first component or the first sigma? Remember, the data is given to you, data is a constant. Okay, what we are searching over is candidates for the k dimensional subspace that will best fit. So what can you say about the first sigma?
We are just taking the Euclidean distance of the x vector.
Correct, and hence anybody? It's constant, it is independent of s. So we are looking for the best s. So this term is not going to matter. This is going to be the same for every s, right? The only thing that changes with the subspace s that you choose is the second sum, the minus sigma x over x, the sum of projections square. Everybody with me? The first term looks like a very critical thing about the data. Yes, it is the total energy of the data, but it's the same data, so it's going to remain the constant. The data is given to you, we are going to find the best fit subspace. Okay, so the first term doesn't matter, because we really do not care about the minimum value that much, right? We only care about which s minimizes the value, and that can be found by checking which s maximizes the second sum, because there is a negative sign there, right? So arg min over error is same as arg max over the sum of length squares of the projections. Okay, so this is again the maximization, the search space for S is the same. We are going to search over all k dimensional subspaces. Think about this picture once more, right? I said I'll rotate this line because now we are searching for a one dimensional space in a two dimensional plane. We will rotate this S along and then calculate the error, the sum of squares of errors, and try to minimize that. Instead, alternatively, what we can do is you do the same rotation and searching, the same search space, but now you calculate the sum of projected length squares and take the maximum. Take the line which achieves its maximum. Okay. Now this view, first of all, this is what is how SVD is going to be computed using the second view, but it also, more than this, the computational part, it gives you a different idea should come to your mind in terms of this is what we really mean when you say maximum information of the data is captured. Almost every amount of energy in the data is there, because when a projection is very close to the data, that is when the distance of the perpendicular is small. Okay. So you can think about this as something which minimizes the error or something which maximizes the faithfulness of the representation. Okay, these are equivalent views. Okay, minimizing the error in this approximation is equivalent to maximizing the faithfulness of this representation. Okay. Okay, so now in order to get it into a more formal set of equations so that finally you can implement the equation in a computer, I would skip the final part of how that actual optimization is done, but now I want to be able to express all that as a neat formula. Okay, this arg max over S, this thing in the red, I want to be able to express as a neat little formula. Okay. So we will work with a special case now. We are fixing k equal to 1, which means we are searching for the best fit one dimensional subspace, equivalently the best fit line that passes through the origin, best fit for your data. Which line through the origin fits your data best in the formal sense that we defined before. Okay. So here, I mean, the setting is the same. Your data points are x1 to xn, all are points in a d-dimensional space. Okay, the ambient space is d-dimension, not, you can imagine 3, but yeah, it could be general. Now we are searching for this best fit line through the origin, right? As we already said, for a computer or even mathematically, the way to pinpoint this line is to take a unit length vector along this line. That's enough. That tells me the line, right? Because the whole line is nothing but all scalar multiples of this line. So the search for the best line I am now going to do as a search for a unit vector. So if you go back to this picture and remember that you were rotating this line and finding the best line, right? Now how am I going to do it in a computer or in a formal mathematics? I am going to take a unit length vector v, okay, of length 1, unit length vector, and the line will be generated by taking the linear combination, the span of this, and I am just rotating this vector along. Okay. So instead of searching for a line, I am just searching for a unit length vector, but I haven't really changed anything. The distance did not change. The distance is still not to the single vector's head or anything. The distance is still to the entire line spanned by the vector, but in order to be able to express it formally and also to put it into a computer, I will think that I am searching for a v such that span of v is the best fit line. Okay, that's the new way I am going to approach this problem. Okay, so that's what I have written. This find a vector which is of unit length such that the span of v is the best fit one dimensional subspace for data. So only a minor change. Okay, there's nothing serious has happened here. I am just finding a representation for the one dimensional subspace in terms of a unit vector. Okay, but even though I say so, it really helps me write a formula for the projection's length. Remember, our cost function involves finding the length of the projection and squaring it up. Okay, so do you know, like in this picture, how can you compute? So this will be your x1's projection on S, right? So what is this length? From your vector, physics vector memory, you should be able to tell me what is the length of this vector. If you know the length, if you know x1 and v. So you know, I'll come to you, you will know the length of x1. In fact, you know what is x1, you know what is v. Can you tell me a formula for this length that I have indicated in orange here? The length of the projection. Okay, this length is, yeah.
X transpose V upon mod of X.
Yes, okay. The answer that I got was x1 transpose v upon, actually mod of x is not needed, yeah. Right? Mod of x, it should have been mod of v, but already v is a unit vector, okay. In general it would have been norm of v, right. This is the computer science view also in some sense, right. I would rather say this as inner product of x1 and v, it's the same, okay. The x1 transpose v will be inner product of x1 and v, right. It's x1 1 times v1 plus x1 2 times v2 plus etc. x1 d times vd, right. This inner product is sigma sigma x1 comma j. Remember x1 comma vj, j running from 1 to d. Remember x1 is a d-dimensional vector, v is a d-dimensional vector. This is the inner product, okay. So this is, in fact I should take the magnitude because now I am talking about the length. Okay. So now I have a cute formula for the length of the projection. Okay. So thinking about representing the one-dimensional space as a unit length vector in that space also has this advantage. Now your length of projection is just the inner product. But more correctly, you should think of this projection also as a vector, right. It's not enough to really say that the projection is this length. Projection also has an angle, right. It's going to be in the same direction as v. So if I want to write a formula for the projection, not just the length of the projection, but thinking of it as a vector, how would I write it? I know the magnitude of the vector, right. The magnitude of the vector is inner product of x1 with v. What is its direction? Same as v. And v is a unit length vector, so I can just write v here, okay. I am not writing an arrow over v, okay. V is a unit length vector, so magnitude is inner product x1 v and its direction will be along v. What happens if the inner product is negative? Is this formula correct? Inner product could be negative, right. For example, if you had a point x, say x6 here, right, then when you drop a perpendicular you will get something here, and if you calculate the inner product of x6 with v, it will be a negative number, but that still keeps the formula correct because v, then it's going to be a vector in the opposite direction of v, so you really need that negative sign, okay. Yeah, so using Pythagoras we converted the distance of the orthonormal to the length of the projection, and using this unit normal along the subspace you can convert this length of the projection to a simple inner product, okay. That's what we have done so far. And now I am going to do this inner product in bulk, okay, like any computer science person will do. I have to find n distances, there are n data points, so I have to find n distances. So I will stack up all these data as a rows of a matrix, okay. So you build a matrix A, first row is the first data point, the second row is the second data point, and so on. So what is the dimension of A? Row by column, what would it be? How many rows? N rows. How many columns? Yeah, so I think you understand what this is, right? And as the answer from the, what is your name? Srihari. As Srihari had said, right? One way to think of this inner product x comma v is as x transpose v. So once I write x itself as a row vector, right, I don't need to take the transpose also, and x transpose v in this case is the first point in the matrix product that I have written here. Okay, can you stare at this matrix equation and verify that? I have each row of A to be a point in x, and what am I multiplying it with? I am multiplying it with a column vector v, and I am calling the result as w. Okay, the result, this is a d rows 1 vector, the result will be an n row 1 vector, right. So what is the first component in the answer in that in the product matrix? Product matrix is going to be a column vector. The first entry in that is going to be inner product of x1 with v. Are you with me? Okay, x transpose v will be that. Similarly, the second thing, right. So in one matrix multiplication, I can capture the calculation of all the projection lengths. I'll have to take a magnitude and all, that's fine. In fact, I'll have to take the magnitude and square. We'll do that in a while, okay. But is this clear? In one matrix multiplication, because it's not enough for me to get the projection of x1 alone. I want the projection of x1, x2, x3 all the way up to xn. One matrix multiplication gives me all of that. It's just A. Now A, every row of A is a vector of x. It's a matrix times V. Okay. And with all these projected lengths, what am I going to do? I am going to square them and add, right. That is what we want to minimize. Remember, what we wanted to minimize in this alternate view was the length squares of the projections. Okay. Which means I have to take this resulting column, the W vector, square each entry of that vector and add, which is equivalent to taking its Euclidean norm or norm squared, right. Sum of squares of components of a vector is square of its norm. Okay. So this thing that I am after, okay, this is what I want to maximize. Remember, this is not the error, this is like that total energy in the data minus the error. So this is something which I want to maximize, but that turns out to be just norm of AV square, where A is the data now represented as a matrix. In fact, people call this the data matrix. Okay, this A is sometimes referred to as the data matrix. If you see some other videos, some people may think of each column as a data point, and then you will have to multiply V on the other side and so on. I am just sticking to one convention. This is probably the more common convention. Okay, but what I want to appreciate at this point is that this entire geometric intuition that we have built up so far is somehow summarized in a matrix vector multiplication. We are supposed to maximize what is in this orange circle. That gives you the best, or that gives you the normal vector along the best fit one dimensional subspace for your data. Okay, the whole thread of the story has to be in your mind. Don't understand things in pieces. Okay, the beauty is in that whole connection. Okay, so summarizing, the task remains the same. You have n data points in a d-dimensional space. We have to find this unit vector, which is whose span is the best fit one dimensional subspace. And what is the solution? You write your data matrix like this A, where each row of the data matrix is one data point, and you solve for which vector u. You are looking for your answer, I will call it as V, and so during the search, the candidate vectors I am searching, I am naming it as u. You are searching for that vector u, which maximizes the norm of AU. Okay. In the previous slide, it was norm of AU square, but since norm is already a positive number, maximizing it square is same as maximizing itself. In fact, when you implement it, you actually maximize the square because you can differentiate it. It's like a very well behaved function, it's an analytic function. You use what is known as a quadratic program to actually minimize this, right? But so in practice you will maximize this, but since you are only interested in the arg max, you are only interested in which vector you maximize as this, whether you keep the square or not doesn't change the answer. Okay, so and this vector that you get, which is a unit vector along this best fit one dimensional subspace, is what is known as the top singular vector of your data. Okay, so you should have couple of things in your mind. Firstly, you should have in mind what do you mean by a one-dimensional subspace or the line through the origin that best fits your data, and then you should see that okay, that is also best fit in both the senses. It kind of minimizes the total error, and it another sense it maximizes the projection. And how do you find this vector? If you write out the formula for this total sum of projection length squares, it turns out to be calculating the norm of this AU, where U is a unit vector along the space you are hunting for. So the whole problem has reduced to finding a vector that maximizes AU's norm, where A is a matrix, right? This is, I'll skip how this maximization is done. This is done using a technique called as quadratic programming. It's a standard trick in optimization. You can do this search because it's like all well behaved, it's a convex thing, you can differentiate and find out. So this is the top singular vector. Okay, this, if I go to our first slide, right? Now I hope you understand this part, right? V1 is the top singular vector. And what is the property of that top singular vector? That is the best fit one dimensional, the span of V1, the line that V1 generates, the line along which V1 lies, is the best fit one dimensional subspace for your data. Okay, so we are ready to go to the next singular vector, right? Any questions so far? Okay, this matrix formulation, I would recommend that you kind of go back and maybe see the slides or work it out yourself, because since I have already prepared the slide and I am telling you it looks very smooth, but even if I had actually done a presentation without the slide, it will take some time to fit all these things into a matrix multiplication and get it correct. Best way to learn is to do it yourself, have the geometric idea in your mind and derive this final form of the optimization by yourself. Okay, derive this final box by yourself as an exercise. Okay, so now we will move on to the general case. Okay, so here I am mostly going to I'll tell you how it is done, and then for so I will can I okay, I think I can take a break now, okay, because otherwise it will be another 10-15 minutes before okay, so we will come back after the break. We will see the general case, okay, but I had somewhere down the line we'll come back after.